Oh, did you adjust it or something? You give me.
Yeah, just move.
Oh, you can move it like this.
Almost.
Yeah. So let's do that. You can put. There we go.
All right.
Oh, there's something in it. Anti-shake, the shake cancellation thing. But yeah, just go ahead and pan it over. It's a little stiff here. I'll loosen it just a little bit. There we go. We started back? Yeah. Okay. So, if we included, let's focus back, guys. If we included the boy and the cart, you would see two vectors of force, and they would cancel out and equal 0, and that wouldn't be interesting. But if we want to study it more carefully, what we could do is write that the mass of our system, which is the cart, equals the sum of the forces, and there's only one force. That's the force the boy is exerting. So if the boy is exerting, say, a 13 Newton force, and say the mass is 2 pounds, or 2 kilograms, then we can work this out. 2 kilograms. Acceleration, we don't know what it is. That's what we're trying to find. And the force is 13 newtons. Okay. Now we can divide both sides by 2 kilograms. You panned over? Mm-hmm. Okay, 2 kilograms divided by 2 kilograms. Well, in order to see the units cancel out, you'll have to actually break up the new units into their what do they call it? Base units. That's kilogram meter per second squared divided by 2 kilograms. Now the kilograms cancel, and what are you left with? What kind of units are those? Meters per second squared, which is what? That makes sense. And this works. Now acceleration is going to be 6.5 meters per second squared. Real simple. And like I said, this kind of almost becomes overkill. You're kind of overthinking it when you do this simple of a problem, but it's still nice to look at it that way. So there's another example. That's what I mean by every action force, there is an opposite reaction force. So now can I erase this? You guys are good? Okay.
Yeah.
I'm going to leave this first one up here because I don't need all that room. Now let's look at another example. I'll give you a book on a table. Now we got to be careful how we label our diagram. What's the system? What are we going to pick as the system to make it interesting? Now let's just look at the book. Okay, so we got here. We're going to label the forces just only on the book. So we got MA equals the sum of the forces. What's the first force you can think of? Gravity. So force of gravity is negative mg, because it's pulling downwards. Now, according to Newton's third law, if this book is not accelerating, what must there be? Yeah, the table is pushing back up on the book and causing a normal force. Now the book also feels, the table also feels the book pushing down on it, doesn't it? But is this part of the system? No, so you got to be careful with that. These extraneous force errors, you might accidentally add them, but remember, the table is not part of the system. But the table has to be pushing back in the book in order for the acceleration. And we call this the normal force, so force of n. So what's the normal force going to, is there acceleration in this example? No. So then this would be equal to 0, and minus mg plus F sub n. So what does the normal force equal? What is it? No? Yep. And does that make sense? What direction is the force, the normal force, pointing? Up. Notice the sign?
Well, why is it changing?
It's positive.
Why is it?
Because up is positive. We called up positive. We don't have to call it positive, but we are.
Oh.
Okay? Now, what is the force of gravity?
It's negative.
It's negative, so it's pointing down. Does this make sense? Yeah. All right. Like I said, wonderfully simple, but sneaky. Now I'm going to do a couple more straightforward examples, and I'm going to end with a hellacious example. Yeah.
What was the Fn on this one?
The normal force. That's the force the table is pushing back on the book. And they call it normal because of normal means a vector that's pointing out of a surface, right? So if you had a Pilates ball, everybody's laughing, and you laid the book on top of a Pilates ball, and what you're going to have is a force vector that's normal to the like if you drew a tangent line at the surface of the ball, right? Or in this case, it's a three-dimensional object, it'd be tangent plane. If it's a tangent plane that I draw on the surface of the ball, the normal force would be perpendicular to the surface, perpendicular to that tangent surface. So that is a normal. What I mean by normal, it doesn't mean normal as in abnormal. It means normal as in perpendicular to the plane of the surface. Or if it's a two-dimensional, it's perpendicular to the slope of the graph. I still have time. All right. Now let me do two more simple examples, and then I want to do just probably the gnarliest one. You'll never see it, but I want to, for the sake of completeness, and like I said, I'm in kind of pedagogical gray area trying this. Maybe it's a bad idea, but I'm going to do it anyways.
That's what I know.
Okay. Another simple example. Free fall with friction. So you got a skydiver jumps out of an airplane. Sorry, that doesn't look like a skydiver, but I don't care. What forces are on it?
Gravity. Air resistance.
Yep. So minus mg and plus the force of friction.
Plus however velocity.
Now this is a function of velocity. This gets bigger as the velocity gets higher. As a matter of fact, I could write it out explicitly. I wanted to keep it simple, but here we go. I want to write it out explicitly. Plus, it's some constant times velocity in the y direction. That actually becomes a differential equation. You can solve for this. The dv dt we'll just call it v. You can take the integral of that thing and find out that it's a natural log and all this other stuff. I'm not going to go through. If you want to work that out, just write this out. And if you, but you'd have to have an integral. I think only one person actually completed calculus, right?
Yeah.
You finished?
Yeah.
If you want to work this out and make it a function of time, you're cool. Okay. You can do it for fun. But that's all I'm going to say about it. I don't want to get into details, but as time goes on, the only point that I do want to make with this, as time goes on, what happens to the force? From rest, dropping it. It gets bigger, so what's going to happen to the acceleration? It slows down. And when the skydiver reaches terminal velocity, is he accelerating anymore? No, that's because the force of friction from air equals the force of gravity. Now this only approaches as an asymptote, so it never actually completely reaches the force of gravity, but it approaches it very rapidly, and then it sneaks up to it, infinitesimally. That'll give you a hint as to what the solution to that will be, because you can kind of already see it by doing a little thought experiment. So that's another simple example. So this would be at when velocity, because this is a function of velocity, when it's at terminal velocity. So when it's at terminal velocity, that equals 0. Before that, there is acceleration. Yeah.
Could the air resistance ever get like big enough to slow you down? Like
No. It'll just keep you at a constant velocity. And you never actually get here. It would take an infinite amount of time to actually get to where this is really 0. Theoretically, you know. But it gets so close that you can neglect it.
What if you slightly speed up?
What would cause you to speed up?
A rocket stuff.
Oh, a little rocket. Okay. Then it's a different problem because then you have more forces, right? You have a thrust force now. So now one more. Really, this is even simpler maybe than this example. If you have like a block on the ground, you're pulling it by a rope, right? Is there a force involved in that?
What's it on his neck?
Can the box accelerate? Yeah. Depends, right? The correct question is it depends on what the force is. Check this out. Okay. So what are we going to pick as the system here? Only the box. Now we see is this rope an external or an internal force? Very good. Okay. So we say MA equals the sum of the forces. Lost my A there. So sum of the forces equals, we'll call this the positive direction, that's tension. We'll just call it T. Nah, I don't like T. I'm going to use T as kinetic energy in this class. Let's call it the force of friction. And then, so that's in the positive direction. No, force of tension. Sorry, I made a mistake. So what's the force in the opposite direction? The friction, force of friction. Now, there's 3 scenarios here. There's a scenario when can you pull on a heavy box that has friction and have it not even move? Yes. In that case, what's this term here? 0. So in that simple case, the force of tension equals the force of friction, because you could rewrite this as force of tension equals the force of friction, right? Now let's look at another case where I'm pulling and it's just I got it moving, but it's not accelerating. Is that possible? So is this still the same?
Yeah.
Even though it's moving, what's MA? 0. Can you guys, I need to make sure you understand that something could be moving and MA is still equal to 0.
acceleration is 0.
Because the acceleration is 0. Now, what about, can you pull it even harder? If you pull it harder, then the force of tension is greater. So then the force of tension is greater than the force of friction. What's going to happen to the box?
Accelerate.
It's not just going to move, it's going to accelerate. So there's some leftovers there. So then you can actually solve for that, what the acceleration, if you know, if they say the force of friction is 10 newtons and the force of the tension of the rope is 15 newtons, then you can see that, I wrote this backwards according to this thing right here. Force of tension is 15 newtons and the force of friction is 10 newtons. Then MA is going to be equal to 5 newtons. And you can just solve for that. If it was a 1 kilogram mass, then the acceleration would be 5 meters per second squared. That should be trivial, right? If mass is equal to 1. Anybody not get that? I'll do it slower.
So what is the definition of the Newton?
Newton is 1 kilogram times 1 meter of an acceleration of 1 meter per second squared is equal to 1 Newton. That's the definition. I put 3 lines there to say that's the definition. Yeah? Good question. Do I have time for my no, because this last example would take. Maybe you were spared. Maybe it was like fortuitous.
It was destined.
You guys want to see it?
Yeah.
You want to see that? Okay. All right. Is that still rolling?
Yeah, still rolling.
Hey guys, get quiet again because everybody wants to see the gnarly one. Okay. This is pretty cool. I want to make a comment. Like, I need to be totally silent here. It drives me nuts. If I shoot a cannonball, you know that it's going to have a trajectory like this, right? Okay. Now, if I shoot a cannonball that explodes in the middle of the air, like this, is there any forces on that explosion? Any external? Let me clarify. Are there any external forces on this, acting on this bombshell other than the force of gravity?
The original velocity.
Is that a force? The velocity, is that a force? That was already given. That's what got the thing moving in the first place. External force. Is there any other external force besides the force of gravity? Yeah.
Like air pressure.
Let's ignore air resistance. And most, I would say for 99.99% of the problems in the book, there's and that might be all of them. There's no air friction. There's no kind of friction. The only time there's friction is when we do these dragging the box kind of things. We'll actually say there's friction. But other than that, there's generally no friction. Yeah.
Would the explosion be an internal force or external?
What do you think? If we drew a box around it, what's the explosion? Is that external or internal? Internal.
There is no force.
Yeah. So does the explosion change the physics? No. So this is trippy. If you calculated the sum of the forces here, other than on this system, you're going to get the force of gravity only. So that means the physics doesn't change for this projectile motion. As a matter of fact, if you tracked it, it ends up that the center of mass of this of all these particles that flew out from the shell exploding still follows this trajectory.
So it's still gonna go.
Yeah, let's see if I can find the little quick video.
Wait, so if it's still following the course, would the pieces still go there, or but since they're being blown away, what will happen?
Hold on. Here it is. Check this out. Lights. Check this out. Watch, he's throwing the racket. Now what they've done is painted some fluorescent paint on the center of mass. So watch what happens. That's the racket. What do you notice about the fluorescent paint? It's just a point mass, right? Just traveling in space. There's a wobbly disc. He's going to spin it. He didn't throw it very good. He got a wobble on it. That was, but you see at that time it was very smooth. You can, here, let me do it again. When he threw it the first way, it kind of tumbled. It wasn't rotating in a plane. So that's why it looked like it was moving, but he got it right the second time. So look, see if you can see the center of mass when they throw these objects. So that's kind of watch where it is.
Would that be part of the grid?
And see the thing wobbling? What was it?
So it's really spinning like a roller.
In the sense of size.
There's the rod. That was the best one, right? Now this one, he kind of threw it to where it wobbled. So it didn't work really good the first time, but they do it twice. So you see a little wobble there. But watch him, he'll throw it again. That one.
It's really hard to pick out that ball.
Yeah. Okay. So now can you see? Now can you see that? Now can you see the shell when it explodes? The center of mass would just continue to take the same trajectory. There's no external force. If I define my system as being, is the bell about to ring? How much longer do I have now?
3 minutes.
3 minutes? Well, let me I'm not going to have a chance to do the whole example, but check this out. If I have a rocket and it's got exhaust, a little fire coming out here, and I make this whole thing a closed system, is it interesting? Nothing moves, right? Is momentum conserved in a closed system with no external forces? Yeah, so look what I have. P dot equals 0.
Wait, if gravity would be an external force?
We're in space for my rocket. That's why I kind of pointed it sideways.
Although there still is gravity.
Yeah, we'll just say we're in the middle. We're at a point where all the gravitational forces from all the galaxies cancel out.
Okay.
Like in the center of the universe.
Yeah.
But then again,
The center of mass of the universe. There you go. There would be no gravity at the center of mass of the
Well, the
universe.
center of mass of the universe would basically be in the center of the universe.
Yeah.
but then there is no
That's assuming that isotropic distribution of mass. All right.
But how
So
would
yeah, I
there,
get to do my rocket.
but how would there be a center of the universe?
What do you mean?
Okay, no, you said
You think the universe is infinite?
is it?
No.
No?